Okay, the next application of exponential growth and decay that we're going to look at is radioactive decay. When we have a radioactive element that's decaying, the amount that's left, or the decay, is based off of the amount of material that's left or present at a moment. So we have the differential equation dy dt equals negative kt, and then integrating that using separation, it takes us to this model that y is equal to y sub 0 e to the negative kt, where k is a positive number, and that shows the decay of any radioactive element. So the first thing we're going to do with this is we're going to come up with a formula for the half-life, how to calculate the half-life at any moment for any radioactive material, as long as we know its rate of decay. So we'll start with this model that y is equal to y sub 0 e to the negative kt. And half-life is how long it takes until half of the material is remaining, or how long it takes for half of the material to decay. If half of the material has decayed, that means that the time that we're looking for is when half of it is left. And that's going to be the key to finding this formula. We're going to let half of the material be left, and that is going to be our value that goes in for y. Well, if the initial amount is y sub 0, when half is left, that means half of y sub 0 is left. And so we're going to divide both sides by y sub 0. And we get 1/2 is equal to e to the negative kt. And now we're going to go ahead and solve this for t, and that will give us the time for the half-life. So I'm going to take the natural logarithm of both sides, because the natural log of 1/2 is equal to negative kt. And then we're going to divide both sides by negative k, and so t is equal to natural log of 1/2 divided by negative k. And doing a little manipulation here with logarithm rules, this is t equals natural logarithm of 2 to the negative first power over negative k. And then we can bring the negative sign out in front of the natural logarithm. And we end up with this formula for half-life, that the time is equal to the natural logarithm of 2 divided by k, where k is the constant representing the rate of decay. So that's a formula that you can either memorize for half-life, or you can just go ahead and calculate it using a similar concept. You guys should know me by now that I'm not a memorization person, so I tend to just go ahead and go through the approach and solve this model every time. Alright, let's look at a couple of examples here based on radioactive decay. Example 2, the decay equation of a certain radioactive element is y equals y sub 0 e to the negative 1.6 t, where t is measured in years. What is the half-life of the element? So I can go ahead and use this formula up here if I want to, or I can just go ahead and derive the formula for this particular constant. You know what, let's save ourselves some time. Let's just go ahead and use the formula. So the half-life of this element is going to be t equals the natural log of 2 divided by k. In this case, k is the positive value of that decay constant. That's 1.6. And so I will just go ahead and break out my handy-dandy calculator and take the natural logarithm of 2 divided by 1.6. And the half-life of this element is going to be 0.433 years. And again, I could also have attacked this by just saying, okay, we want to figure out the time when, there we go, and we're down to half of y sub 0, and simplifying that algebraically, and natural log of 1/2 is equal to negative 1.6t, and so t is equal to the natural log of 1/2 divided by negative 1.6, and then I could have calculated that. Natural log of 1/2 divided by negative 1.6, and I get the same value for t. Alright, now this concept that we just did is more applicable to other situations in decay than just using a formula, and we're going to use that in part B. Part B, how many years will it take for 96% of a sample of this element to decay? Okay, so think about what that means. If 96% of the sample has decayed, that means 4% of the sample is left. So we're finding the time when 4% of the initial sample remains. And so we want 0.04 of the initial sample to be the amount that we have at a given time. And so we'll substitute that in for the amount. And now we'll go ahead and solve this for t. We divide both sides by y sub 0. Take the natural log of both sides. Divide both sides by negative 1.6. And then we can calculate the time. And I've got natural log of 0.04 divided by negative 1.6. And it should take 2.012 years until we're left with 4% of the sample, and therefore 96% of the sample is decayed. Alright, that's the end of this lesson. See you guys next time.